First of all, I would like to thank the organizer giving me the possibility to report on some recent results. Jointly with Lubomir Banaš from Edinburgh and Czislaw Brzeziak. For me personally, it's a very pleasure that I made acquaintance to Czislaw 2 years ago on a conference in Trento, and to have the possibility to work with him, for instance, in this project. So the goal is numerical analysis for stochastic Landau-Lifshitz-Gilbert equation. And it seems to me that in the spirit, I'm not talking about some technical results here, but in the spirit, it's not too far away from the talk which has been given before by Martin Heira. So the goal is to construct or to come up with a discretization of a problem, which is given here in the third line, such that this discretization is able to construct weak solutions. So I'm not relying on regularity properties of solutions. I'm not relying on some bands of eigenvalues, for instance, which are small or big. So I would like to have a practical scheme which I can implement to the computer, such that in some sense or the other, the solution converges to an object which, by surprise, is a weak solution. Okay, so my talk is split into maybe 4 parts. It will take some 10 minutes or so to discuss the Landau-Lifshitz-Gilbert equation, which is a continuum model to describe ferromagnetism. So after 10 minutes or so, we will step over to the deterministic Landau-Lifshitz-Gilbert. So far, nothing about stochastics. And I will report about on the problems which arise already in a deterministic setting to construct a finite element-based discretization, which is in the limit constructing weak solutions of the LLG, Landau-Lifshitz-Gilbert equation. So this will take us maybe some 20-25 minutes, and the rest is about the stochastic Landau-Lifshitz-Gilbert equation, where some stochastic phenomena have to be accounted for as well in the construction process of a numerical scheme, which then will construct some Martingale solutions for vanishing discretization parameters. Okay, let's start with the motivation. If I go to the internet, I see some photographies taken by physicists with a polarization microscope. And we observe some areas which are black and other areas which are white. And it seems that they are separated by a sharp interface. So in fact, what this optical photography is telling us that is that in the white areas there are some spins sitting or some magnetization arrows sitting, which maybe, for instance, look from bottom to top, yeah, maybe some small fluctuations, and in the dark area there are some spins, or there are spins, magnetic spins, which look in an opposite direction, say from right to left. So, and it seems that there is a sharp transition taking part here, and we would like to understand, for instance, dynamics of ferromagnetism, which is important, for instance, if it comes to designing hard disk drives, etc. So there are lots of effects, nonlinear effects, which physicists are well aware of. They talk about remanency, so the resistance somehow of the material towards some magnetic loading, as far as I remember, and some time delay effects are also observed in practice. So the model that I would like to discuss in a second goes back to the 1930s, to Landau and Lifshitz, so very, very old model, and still of interest for us, for instance, nowadays, if it comes to hard disk drive constructions, etc. So Of course, in experiments, you cannot do the following. You cannot take a ferromagnet and take a scissor and cut it and have a look and you see the domains, right? So it would be a quite interesting idea to model such interesting behaviors in a ferromagnet and maybe by a continuum model. So I would like to discuss on the next 3 slides different scalings, different effects which can happen. And the first one, you see I made a mistake, so you have to change these 2 arrows here. This one is a picture of a platelet, of a ferromagnetic platelet. Think about you are living in New York and there are lots of skyscrapers, and one skyscraper is bigger than the other one. So depending on the height of such a skyscraper or bungalow, there are different so-called ground states, magnetization patterns, which you observe, and so you see an interesting interplay between geometry and magnetization patterns. So the experts talk about Landau state. No, I'm sorry. Yeah, this is Landau state if I would have drawn it correctly. This is diamond shape ferromagnetic pattern, which is energetically favorable. And this is so-called S state, and this is so-called flower state. So depending on whether you are living here in a bungalow or in a skyscraper, skyscraper, you get different magnetization patterns. So it seems that there is a sharp transition between these areas of preferred magnetizations, which are called Weisschen domains. But if you zoom in the area, for instance, here the transition between the guy looking here from left to right and here from right to left, you observe that there are on a smaller scale some diffuse interface transitions, some continuous transitions taking part. And again, depending on geometry, we have some Bloch walls or some Néel walls, which are observed, or some more complicated wall structures. I would also address here the non-stationary phenomena, and this is known as precession. So if you put your finger on one physical place X of your ferromagnet and apply a load, which is here H effective, and this is H effective in exterior field, so then you observe some precessional motion at this physical place X. And this comes to an end at some finite time, at least this is observed. By the way, Landau-Lifshitz-Gilbert is a phenomenological model. So you add some dissipative effects, and in the end, putting things together, you get the Landau-Lifshitz-Gilbert equation. So this Landau-Lifshitz-Gilbert equation is a damped precession, is describing damped precession. So very interesting for applications. If you modify your LaTeX file, store it to the hard disk drive, and then you want to modify it, is some switching phenomena. So how fast does it occur to flip information from, say, direction pointing upwards to direction pointing downwards? This becomes, for instance, interesting if thinking about miniaturization. Neighboring patterned structures influence each other. This brings us to thermally activated reversal and a model which uses stochastic components. So if we have a transition which goes like deterministic, or whether there are some stochastic influences involved, this makes the difference between the LLG on the left and the SLLG in the end of my talk. So let me start with the second part, which will take some 20-25 minutes, and which is on the deterministic Landau-Lifshitz-Gilbert equation. So the nonlinear PDE, deterministic, is a constraint for a unit vector field. So I go to every physical space X in my ferromagnet and attach to this one an arrow of length 1. It's very important, for instance, if you think about discretizations. So at every physical space place X, you attach a unit vector. So what is now the constraint in terms of PDE? Oh, by the here is another motivation. Here's a picture of a so-called trace on your hard disk, and you see these patterned media, or these patterned structures. I'm sorry, where you see an average magnetization reflecting binary information. So if you want to make this flip here from left to right, this is very interesting, of course, if you want to speed this up. Okay, but now let me bring my argument back, or my discussion back. We have a unit vector field that we are interested in, and now we would look for a PDE constraint, which is the deterministic Landau-Lifshitz-Gilbert equation. And the PDE constraint is given here, and it's a simplification of the more complicated model of Landau-Lifshitz-Gilbert, but this involves the crucial components for solution theory, right? Existence theory. So LLG. So we see the time derivative on the left, and then we see m cross Laplace m, which reflects precessional motion. So if I would omit the red term, I would observe only precessional motion here, where the h effective in this case would be the Laplace of m. But in practice, I observe some damping effects. So there is a red term, which is of course scaled by the small positive number, and this is another nonlinear term. So we see a nonlinear equation, a nonlinear PDE equation. So let us check for some properties by using formal arguments at this stage. So let us multiply. Let's think about scalar multiplication by m in R3. Yeah, but this is nothing but a half d divided by dt. So thinking in terms of pointwise multiplication. And now this is a cross product structure. So this term is gone, this term is gone. So this guy is 0. So this constraint does not conflict with the constraint which we had in the beginning. So another one is, so we get, let me erase this one again. The first property is the sphere constraint is conserved at every point x of my ferromagnet at all times. So an energy law here comes from variational multiplication by Laplace of m. So the first guy gives this energy contribution. Okay, there's a dt evolved in this one. And so we have to integrate in time later on. So then this, if the red guy here is nothing but m cross Laplace of m, comma Laplace of m, the right sign, and this is nothing but by variational. By vector product calculus, or vector calculus. I'm sorry, it's nothing but this one. So the last term is 0. Why is this the case? A cross B times B, 0. So we get, after integration in time, an energy law. So the most important issues, because I have no space here, I always have to erase this one.
There's some space on the left.
Okay. So the properties, in order not to forget, because this is important for the following, if we want to construct a numerical scheme which is able to construct corresponding weak solutions of this problem. So the crucial properties are a sphere constraint, and the second one is an energy law, and let me write it like this. So once we start with a finite energy, it seems at least in a classical for classical solutions that we have this property here. So if we talk about weak solutions, we want to get energy solutions, which where we have a less equal here. Okay, so first investigations go back to François Zalouche and other people in 92 and Guo Hong, but they all use some abstract Galerkin methods or other methods which are not fully space-time discretizations of this problem and not usable for practice. What does it mean? What does it mean usable for practice? I would like to have a constraint for some approximate solutions, which is a discretization in space and time. I'm not talking only about the discretization, for instance, in space, which would lead to a system of ODEs. And also not, I don't want to use some abstract Galerkin method, which is using some eigenfunctions of some nice operators. I would like to use a method which I can implement. Okay, so the following pictures want to should motivate the following. We have weak solutions of this problem, but there remains the questions whether solutions have maybe improved regularity properties. So maybe they are smooth, and this is an overkill because we have classical solutions. But this is wrong, as you will see by numerical motivation on the next slide.
What about uniqueness and initial conditions? What kind of?
No uniqueness. So for general initial energies, finite. So here's a picture, some snapshots for increasing times, and this illustrates the fact that the weak solution concept is the one that we need. So we have a blow-up behavior here, and the blow-up behavior is as follows. Here we have a zoom at the place where something is happening, which I will now show you with my hands. And the computation by a numerical scheme, which I did not talk about so far, the computation has been done on a larger domain. So think about a bunch of flowers which you have. So you have a bunch of flowers, and there's one guy sitting in the middle looking upwards. So at positive times, so this is rotational symmetry in the beginning, we see that there develops a big gradient close to the origin, and this reflects the third line. It reflects the fact that we have a blow-up behavior, and so we cannot rely on regularity properties, for instance, if we are interested in numerical schemes. In fact, what we also observe is that there is after the blow-up, so first phenomenon, we have a second phenomenon, which is a switching process. I will talk about this later on. Hopefully there is some connection to the motivation which I gave. Okay, so if I want to construct a numerical scheme which is able to reliably approximate the situation, I cannot rely on regularity properties. So what are the problems? I would like to discuss the problems here rather than giving too many technical details. So one problem is that we are restricted if we are using finite element functions. I will show this to you in a minute, what I mean by this. We are restricted to piecewise affine functions. Now think about the situation that you have three neighboring nodes which are discretizing space, and you attach to them arrows of unit length. So then you are constrained already what is happening in between. So you can easily guess that the sphere constraint is violated because numerics is not rich enough. Right? So what do I mean by finite elements? So as a numerical analyst, I introduce a triangulation TH And I'm only admitting boring functions. By the way, all results which I will show to you on the following slides are for the three-dimensional space setting. Although you saw pictures here which are in 2D, right? So the phi is vector valued, and I put here an h, sorry. So these are for every k polynomials of degree 1, less equal 1. So no constraint here, and so then we have the following representation of admitted objects. They can be by thinking about a basis, phi L. I will describe this in a second. So this is phi h at places xl, and the places xl are the nodes. And the basis function phi l is a head function which has the height 1, is only 1 at this node, and is 0 at all other nodes. And it's constrained to be piecewise affine. So the phi L of xm is delta Lm. So this doesn't seem too complicated. So this is the these are the objects which I can use in my numerical scheme. So the question is how to deal with the sphere constraint. This is the first problem, because this sphere constraint, if you look to the problem closer, you see that you need to make a numerical discretization which is respecting a sphere constraint in some sense or the other in order to get an energy law. But this opens the gate then to run normal functional analysis arguments to construct weak solutions in the end. So what we need is we need a discretization which respects the energy law, the sphere constraint and the energy law in some sense. Okay. Another point is we all know maybe that implicit Euler, if we think about discretization in time, is strongly damping. So, but we want to stay on the sphere. So we have to deal with this issue as well. And this seems more standard the second. So I will be very brief on the next 3 slides with 4 different strategies which are now available to overcome these problems. So the first strategy has been developed by François Zalouche and Gesson in 2006. And we did some more refined scaling analysis on this. The idea of François Zalouche and Gesson was the following. If we go back to the sphere constraint, we know that the time derivative of m to the 2 at every point in space and time is 0. But this means nothing more than mt is perpendicular to m. So, and here we have the new increment v, which takes its role as new minus old in some sense. And so this now goes in the tangential direction starting at the point un. So basically what we are motivated to think of the v as u new minus u old. U new minus u old is then perpendicular to u old. And hopefully this will turn to a good scheme then. So this is their idea. What can be proved is that for this explicit scheme, by first dealing with the evolutionary character of the problem, And then, accounting for the fact, I missed by saying this, this new arrow is shrink back to the sphere again. So by first taking into account the evolutionary character and afterwards the sphere constraint, we get a scheme which is doing all what we want. So we get a sphere constraint at nodes, and for delta t, for a scaling delta t, which is very, very small with respect to delta x, what we observe is then convergence, and the limit, by surprise, is a weak solution of the problem. Yeah. So in the sense of subsequence convergence, right?
What do you mean by perturbed energy law?
We get some additional terms. I forgot about them now. But
You have dissipation.
we have some numerical dissipation effects involved in this one. Yeah. So because of the explicit character, we need a balancing of time discretization parameter and spatial discretization. So the second out of the 4 discretizations would be Ginzburg-Landau penalization, which means that we penalize the sphere constraint. But I already told you that we have to expect some blow-up behavior in simulations. So the question in actual bloody computations is how to choose the epsilon depending on numerical discretization parameters. So as long as solutions are smooth, we have no problem to choose a proper epsilon in a numerical discretization problem. But once interesting things are happening, it's not clear how to balance the numerical discretization to penalizing the sphere constraint. So the third strategy, which turns out most successful here, is an implicit discretization. Again, it's a discretization in space and time. And we have here some additional notations, and I would like to discuss the tools which are needed. Tools for third scheme. So the first is reduced integration or numerical quadrature. So in fact, we have a little h at several places. We have a little h at several places, and what it does to the entries, which are elements from capital V, h, on the very right, is the following. There are some well-determined beta L. What is L? These are the places. This is the index set of the nodal points. If you take a scalar product in R3, you simply evaluate the integrand. You simply evaluate the integrand, for instance, at 3 or 4 points. Why evaluating? Think about the picture which I draw to you on the previous slide. So this is for all. So this is a scalar product. The second strategy is to use the so-called discrete Laplacian. I define this again on the very right. Think about the fact that we are constrained to piecewise affine functions, but we have here the Laplace of m. And we discussed the fact that the multiplication with Laplace of m is quite important to get an energy law. So what is the Laplace of a piecewise affine function? So I make a minus here. So please observe that here we have to adjust the definition of Laplace H to the point evaluation, to the numerical quadrature scheme that we are using here. So this is what we mean when you see later on Laplace H of phi H. This is what you mean then, because these, the right-hand side makes perfectly sense. Okay, but then the scheme is as follows. We use reduced integration here, here, and here. And what we can now do is try to copy the strategies which we had here to validate a sphere constraint at nodal points in space, in space-time. And second, to get an energy law. So again, I'm restricted with space. And I try to do this here. Let's do the following. Let's choose phi h m j plus a half. I didn't tell you what this means. Phi j plus a half means the new guy plus the old guy divided by 2. So choose this test function. So xl is a nodal point, and choose phi l. What was phi l? This was a scalar function which is piecewise affine and is 1 at a nodal point xl. So, but then we can start with the first guy, dt m j plus 1, m j plus a half, this is nothing but, we use the definition of h, of, of the, I have this on the very left. We use this definition, so there was a beta L involved, but it is only the place L which survives here because the phi L at place xm is delta Lm. So the phi L at place xm is delta Lm. So what we get is beta L dt m j plus 1 xl m j plus a half xl in R3. But now this is binomial formula, new minus old, and here we have new plus old. And this is nothing but beta L m j plus 1 xl to the 2 minus m j xl to the 2 square. So we have mj xl to the power 2. And this is the norm of the arrow at place xl. But the difference of two iterates, successive iterates, is 0. Why that? Because we have here the structure. Think about the test function which we are using here. We have a structure A cross B times A, 0. And this one vanishes as well. So bottom line is, this is a scheme which preserves the sphere constraint at every nodal point. So now there was another thing necessary, which is the energy law. And again, I apologize. I'm very restricted here with respect to Blackboard. So we choose phi h Laplace h m j plus a half. So Laplace h is applied to a finite element function, element in V, capital V h. And we discussed about the fact that we are sitting in VH as well. So admissible, and now this definition, taking into account the definition here, we get an energy after integration, or after using the definition, I should say, of Laplace h. We get an energy contribution here, and we can use vector calculus again to make this guy here, what is sitting inside the brackets. And then we have to the power 2, and we have something similar to the L2 norm. I'm a bit fast here, but I want to only mention the fact that constructing schemes which preserve important properties is not so trivial. So, but once we have these two properties, so then we can pass to the limit in a proper sense and use all what we know from functional analysis and then construct weak solutions. So the third strategy is a strategy which I give here for the related case of heat flow harmonic map. And the heat flow harmonic map, so this should be actually a little u, is like this, where the lambda is analytically nabla u to the 2. Nabla u to the 2. But if you think about spreading information in space and time by using finite element functions and piecewise discretization in time, I can only tell you that the lambda looks completely different if we want to discretize the problem and think about the discrete sphere constraint. I'm making difference between discrete sphere constraint and sphere constraint in this highly nonlinear problem. So this problem can be solved in the sense that here we use not u to the n or u to the n plus 1, but again we need a combination of new and old. Because we want to play a game of the sort that here we need to take a test function which is time derivative. Time difference. This means u minus old. I apologize for that. U minus old. And we take as test function the same one. And then we have a plus b times a minus b. And this again, if we respect the sphere constraint, the discrete sphere constraint, leads to a scheme which has the desired properties. The difference being that here, in order to prove existence of solutions in a discrete setting, by using Brouwer fixed point argument, we need some constraint between the delta t and the h. But then energy law and the discrete sphere constraint turn out from the construction. Again, bottom line, one has to be careful how to construct discretizations of the problem. So this all was a beginner somehow to now use these understandings for the stochastic Landau-Lifshitz-Gilbert equation. So and the equation is motivated by physical motivations and looks as follows. So we have a deterministic part, and we decided to incorporate a Stratonovich stochastic part to the problem. So there are papers by Kohn and collaborators, but also in the physical community, people are in favor of such a discretization, for instance, using the Stratonovich. So this problem has been analyzed by Czeslaw Przeźniak and Goldies in 2009, and this was actually the meeting point where we started to think about getting a numerical discretization of the problem, such that in the end we can do some computations and see actually what is happening. But most important, we would like to have a discretization which is constructing a weak solution or a martingale solution. So nothing about rates of convergence, only talking about subsequence convergence. Right?
You don't have minus in the front of the...
Maybe. Yeah. Thank you.
What is H?
This is, I apologize, this is exterior field, so which was formerly H effective. So a given applied deterministic field. So it's very important to have this cross product structure here. Because think about formally multiplying the resulting this equation by m leads to conservation again from all the arguments which we discussed before. Conservation of length, because a cross b times a is 0.
And the Wiener process is real. It's a
Yeah, it's
Real value.
it's real valued. Can be generalized, but we considered here the real valued case. Okay, so before detailing more about the key steps in this program, in the top of this page, I would like to address the numerical questions which we have if our program is to come up with a discretization which is constructing weak solutions, which means martingale solutions. Again, three-dimensional setting. Okay, how to realize the sphere constraint for finite element functions in a stochastic setting. So this is, of course, clear that we have to deal with this problem. And the second question is how to identify limit of the stochastic integral. So these are two problems which have to be overcome. So we have a space-time fully discrete problem, or numerical scheme, which I did not mention to you so far. What is a martingale solution in our context here? So we have a 1D Wiener process involved here. And this is the object that we are after. So in this work by Brezheniak and Goldis, they constructed a martingale solution by using a general Galerkin method. So they are not the construction of an approximate is by means of eigenfunctions, for instance, of a good operator, involved good operator. Also, it's only space discretization, but we want to have a numerical scheme, so we are interested in space discretization and time discretization. They have a conservation property, which is not the unit sphere constraint. It's only conservation of the L2 norm in space, which is valid for the approximates Mn. So and then some well-known arguments, let's say it in one sense or the other, are needed then to get some compactness results for proper sequences Mn prime, and for the construction of a limiting object, which by surprise is a solution of the problem. So the numerical scheme here is as follows. We are interested in space discretization and time discretization. So we are interested in getting a discrete sphere constraint, because not just by fun, but because we need this for passing to the limit. So then we get it. We want to have an energy law, or let's say better a priori estimates for this problem. And key problem is identification of a limit of stochastic term. So the difference to the discretization which I showed to you before, which was let's just recapitulate in order to understand this again. This guy here was important to be as a combination of new plus old divided by 2. Why? Because I use as test function something which is new plus old. And this means new plus old, and this means the difference of the modulus from the past and the new modulus, which eventually leads to the fact that we have a discrete sphere constraint. So we need to put here j plus a half. We need to put it here as well to make this cancellation argument. But at this place, we have some flexibility. So here we have j plus a half, new plus old. So in a stochastic setting, we need only mj plus 1. So we have to modify, as explained, this guy here. I will detail this in a second. Why? Okay, and this is the scheme, and this can be implemented, and we will see some pictures later on. So the result is that the computations have something to do with a martingale solution. In fact, they are constructing martingale solutions. So what is needed? A discrete sphere constraint, a discrete energy law. We need higher control of over increments, and then some further arguments which I will detail on the next 5 pages or so. So first of all, for finite kh, we have solvability. So this is a little omega, I'm sorry. So I already mentioned quite a lot the discrete sphere constraint, A out of 4 items, which I will now discuss. So the headline is here, stability properties. So we have a discrete version of energy law. This can also be validated by the arguments which I showed to you in a discrete setting, in a deterministic setting. So the next is to think about higher moments, which can also be quite straightforwardly obtained. Item B is more involved rather than item C at this place. So then what we want is the following result. We need actually, in order to get some compactness going, we need better control of iterates mj, and please observe here the L. There is an L. So we need to control increments for some positive L in such a setting to use to run some compactness argument. And the vehicle to do this is to exploit basically the reduced or the numerical quadrature which we have used, because here this means interpolate this funny object. We are able to write down pointwise equation, pointwise in space. Think about the variational formulation of the problem. Here it seems that we are dealing with a pointwise identity, which is really in fact true. And this is the magic happens from the fact that we are using mass numerical quadrature. This is the key at this place. So then we can translate new plus old to old. At some point we want to apply expectations. And we have some deterministic term here. Please observe the k. And the rest is hidden by this calligraphic A. And this calligraphic A tends to 0. This can be shown. So basically, it's this here says we have a pointwise identity with a perturbed version of a nice stochastic perturbation. And this is the key to then get this result, which is needed to then make a compactness argument. And in order to turn over from time iterates to functions, so to analysis at this place, so we use the function calligraphic m, which is a fine interpolation in time. Not so good for stochastic, but very good for analysis. Right? So we can control this object here, which we constructed, and we can identify limits. The y and the z is what you expect for the deterministic integrals. So, but in order to deal with a stochastic term, the stochastic integral, we still have a problem. So what is the limit of the stochastic part? And for this reason, we modify this construction here, tool B, in such a way that we solve for t, which is between tj and tj plus 1. We are solving this problem, which is now, in some sense, continuous. So you give more freedom to the process m tilde. And what you observe later is that this m tilde, the red guy, is essentially nothing but, I made a mistake here, the red guy is nothing but a slight perturbation of the blue guy. What is the blue guy? It's some sort, this is the stochastic. This is the analytically convenient guy. This is the stochastically convenient guy. Why? Because our last step is to identify the limit of the stochastic integral. Okay, I missed here an expectation somewhere. But basically, we are using this identity. This is the key of everything, which says that the difference between stochastically convenient and analytically convenient is by this guy, which goes with increments of the Wiener process, for which we know quite a lot about Hölder continuities. This is the reason why the delta t to the beta enters here. So we are almost at the end. The rest now goes by in a straightforward fashion. So the most important thing here is that we have now this m tilde kh, which is not so far away from the analytically convenient guy, and we can construct a filtration which depends on kh. So then we pass to the limit with this guy and obtain also a corresponding filtration. So now the most important step is to say that this is compatible in the sense that the limit, which is everything but the rest of this equation somehow. So you see the stochastic part, but you don't see I'm sorry, you see the deterministic integral, but not the stochastic one. So that this is a martingale, and then standard arguments give you a W and the limit identification of the stochastic part. Okay, here are some 4 pages of relaxing computations. So the first one is basically the most uninteresting situation. Let's suppose solutions are smooth. Then we can prove some first order weak strong convergence rates. Okay, this is somehow a test that our scheme is not too bad from a computational viewpoint. More important, let's think about a situation that we have a blow-up behavior, or we want to simulate a possible blow-up behavior. Again, we only can give computational evidence at this place for blow-up behaviors. There are no existing analytical results for blow-up profiles. But we have a numerical scheme which is conserving the sphere constraint and has the discrete energy law and constructs in the limit correspond a suitable solution. So why not turn on the computer now? So what we observe here is that this guy here is found not to explode, rather than if you consider corresponding trajectories. So every single trajectory shows a blow-up behavior, but the expectation, or what you have here, a little different, is finite. So maybe the stochastic part is slowing down things a little bit. Also, I don't want to discuss this one. So also, here you see a zoom of what is happening. So this is in a neighborhood of the origin. You see yeah.
So I didn't quite understand that last point. You're saying that m blows up omega by omega, but the gradient of m squared seems to stabilize.
I made a mistake. So the gradient of m in L2 norm, evaluated in time, pointwise, for every trajectory blows up.
The super overall.
Yeah, think about the picture in the very beginning. Yeah. So the story with the flowers. Yeah. So, but then
after blowing up, it comes back to order 1. I mean, what happens after it blows up?
So then what we observe numerically is this flipping, the switching. So we have these
both at a point, are you saying?
At a point. So there's one guy standing looking upwards, and all other guys are looking downwards at a point.
Yes,
at infinity norm. Energy stays finite.
You continue the solution.
Then I continue. Yeah. So the weak solution is the solution concept, deterministic, and here pathwise. But it seems that the expectations slow down dynamics, in a sense that we don't observe blow-up. No proof, no analytical result, only numerical experiments. Also, we have this the noises of the structure M cross H. So we observe a little movement of things going on in terms of blow-up behaviors. Yeah.
The fact that the expectation of the gradient M square is finite, is that coherent with what you would know about the speed at which the thing blows up?
Say, is this coherent with?
Do you know, so for the deterministic equation, when there is a blow-up, do you know at which speed it blows up?
So in a deterministic setting, we don't know. We have no analytical evidence for finite time blow-up behavior. First statement. Second statement, for the related heat flow harmonic map. I'm talking about mappings going from R2 to S2. So in this setting, there are results, analytical constructions by Struve and other people who evidence a finite time, finite energy blow-up. So this problem is related. And it seems that the same profile that we put here and used for numerical simulations, the same profile as the one that Struve and Yunmai Shen used for the heat flow harmonic map, this produces a numerical evidence of blow-up behaviors. We use again the same profile here for the stochastic setting. These are the observations. Okay, so we observe a switching again. So see this red guy here, and now there is a little bit shame this guy here looking downwards. But also there is now the question about what about the length. So we have the sphere constraint, but think about expectations. So one guy is looking upwards, the other one, the neighboring is looking downward. The next one is looking downwards. So the expectation would be 0, right? So we don't conserve the sphere constraint anymore if we think about expectations. In fact, maybe this is, we see the following. At places where a flipping happens, what does it mean? Or switching. Look this guy looking upwards, look this guy looking downwards, but a different color, red color, green or whatever. This goes together with a reduction of the modulus of E of M. So it goes down to 0. So think about the effective equations for possible effective equations for this object E of M. So and here are some pictures which are not so nicely visible only when you go very close, which again highlights the fact that the length at the origin goes down, and we have some non-trivial rotation effects because of this M cross H and the noise. I have 2 pages of summary. So Landau-Lifshitz-Gilbert is a geometric nonlinear PDE. The goal is to construct, for me as a numerical analyst, to construct a practical scheme. And these are the tools needed to do this. And I discussed in particular the cross product, the meaning of cross product and reduced or numerical quadrature, I should say, not reduced integration, but numerical quadrature. The role of cross product and numerical quadrature, together with the discrete Laplacian here, which are key tools to accomplish this goal. And here we have the stochastic setting, where we needed a reformulation of our numerical scheme, which is in the end constructing again related meaningful solution. Thank you very much for your attention.
Well, so again, so regarding this blow up of the gradient of M, so if you compute a higher moment than the second moment, that would probably be infinite.
No, we didn't. We didn't. A good point. We could try to understand this more.
If you know at which moment you have the transition between finite moment and infinite moment, it actually also tells you the exponent at which the blow up.
Could be, yeah.
I mean, there's a relation between the two.
Yeah. So I expect that this is observable for all. Also, if you think about here we computed the expectation of the gradient of u in L infinity. If you compute this in LP for p bigger than 2, then you already get the blow-up. We tested this for different discretizations and triangulations to hopefully observe a robust phenomenon. And but that's a good point. Yeah.
Thank you very much.
Thank you.